All right, let's try this again. I think we're working now. So I accidentally fiddled with a cable. Turns out everything is just that finicky. All right, I'm gonna start.
There might be an easier way.
All right, hello everyone. Shh. Hello. All right, we're gonna start the transport crash course now. So yeah, I guess I'll give you guys some like kind of exam tips and stuff first, I suppose. So my general take with this course, so I did it last year, so this was the paper I did last year. I think it is a reasonably like medium difficulty course. I don't think it's like a walk in the park like 2101. I feel like 2101's a lot easier. I think what makes this one hard is it's closed book. It is still closed book, right?
Yeah.
Yes, yeah. It was closed book last year. I would be surprised if Divya made it open book. So I think that makes it kind of hard. And also I think there's just a lot of concepts in it. It's a very concept heavy course. It's not really like steels and concrete where each week kind of builds on previous weeks. But then with that said, like I feel like if you do the past papers, you should be pretty well covered. Let me turn off that. You should be pretty well covered as long as you do the past papers. So I'm going to go through 2025 and then just remind me at the end, I might forget, but at the end, so Sue last year went through the 2024 paper. So Divya hasn't given you guys the 2024 paper, but I will link it at the very end somehow. I'll figure that out later, but I'll give you guys the 2024 paper, and Sue went through it, so I can also link you to her explanation. So if you just do those two papers and then the other two Divya's given, obviously if you do the paper I'm going through right now and then Sue's one as well, you'll be able to do it, and then you can look at our solutions. So it should give you a pretty good base for the paper. I also heard, I think like everyone did pretty well in the midterm, is that right?
Yeah.
So I think that means knowing Divya, she might make the final harder. Hopefully not, hopefully I'm wrong. But like, so I've done 2 courses with Divya, and she's a pretty good lecturer. But just from my experience, her exams, they're not necessarily the easiest. I hope by warning you guys, then it ends up being like, you guys end up being well prepared for it. Yeah, I feel like she does have a tendency to not necessarily, kind of curveballs, not even necessarily curveballs, just like, it's not always cut and dry with Divya, I think. I think she does tend to spice up the questions a bit, and I think she underestimates the difficulty of questions sometimes. I remember she once said the course I did, the elective I did in term 1 was, some people do as a WAM booster, which is insane. It was not a very easy course. Yeah, so in terms of other tips, just there's not really anything else, to be honest. I guess revise the formulas, try and have your own set of notes. I know the transport exam's on Tuesday, so you got about a week. So try and do this paper, and then I'll also link the 2024 paper. Yeah, let me make sure it's all recording. I think we're good. Okay, I get paranoid because once I did it and it didn't record and I had to do it again when I got home. Okay, so basically today I'm just going to go through the 2025 paper. I did it all yesterday. I'll link you guys to the actual solutions as well at the very end. So if you're watching the video at home, I'll make sure there's a link somewhere. Maybe it'll be in the description, or maybe it'll be a QR code or something, but I'll make sure you guys can actually look at the solutions itself, not just like you have to scroll through the video. Okay, so I'd actually rather go through the harder questions as opposed to the easy ones, and then if we have time, we can come back to the easy ones. So this question is relatively doable. This is almost, I would say, 3 marks. It's just a like speed density question, using like the relationship between speed and density and traffic flow. There's not too much to that one. It's so I would like to just kind of skip through that one, but hopefully if we have time at the end, I just don't want to lose time for the harder questions. I'd also say question 2 is pretty straightforward. So I wouldn't say this one's too hard. So again, I'm hoping we have some time at the end and we can go through it. So I think we're going to probably do 3, 4, 5, 6. I think there's 6 questions. Is it 6? Let me just check. I think it was 6. Yeah, so we'll probably do 3, 4, 5, 6, and then we'll come back to 1 and 2 at the very end. So if you're watching at home, just that's the order we're going in. All right. Cool. So question 3 is, this is the first half. So question 1, 2, and 3 are like the first half of the course, and then 4, 5, and 6 are the second half. So question 3 is, A simplified road network representing 4 key locations in Sydney CBD is modelled with 4 nodes labelled 1 through 4. The nodes are connected by bidirectional links with the following travel time functions for each link. And we've got Tij equals Aij plus Xij, where Aij is the free flow travel time in minutes on the link, and then Xij is the flow on the link in hundreds of vehicles per hour. Okay, so I just want to point out, and this is where you can slip up in an exam, that it says hundreds of vehicles. Your calculations will be very off if you miss that, which you'll see in a moment. So make sure I think transport tends to do this a lot, where it's like, it's actually thousands or it's actually hundreds, so just make sure you pay attention to that. Okay, so these are all the equations that we've been given, okay? And what these equations basically represent is, for example, I'll zero in on T12 equals 4 plus X12. So that basically just means the amount of time it takes to travel from 1 to 2 is equal to 4 plus the number of vehicles on using that path divided by 100, basically, okay? It'll make more sense in a moment when we go through an example. But it's literally saying as you add more cars, the time goes down. So for that example, if we had 0 cars, it'll take 4 minutes, okay? Because 4 plus 0, right? If we had 1 car, suddenly well, it's not plus 1, it would be plus 1 over 100. So let's say we added 100 cars, it'd be 4 plus 1, which would be, it'd now take 5 minutes to go from 1 to 2, and so on, okay? So the origin destination demands between the nodes in vehicles per hour during the peak periods are given below. Assume that the transport network is empty, that is, flow Xij on all links is equal to 0. For each OD pair, determine the minimum path tree and clearly list the chosen path for each OD pair. So this is, I think this is what I mean about transport, is you've just been dumped with like a whole page of information and you have to just kind of distill all of it. And it can be a bit daunting. So what I would do first, I'll just check. What I would do first is I would draw a diagram. So what we do, we've got so I actually drew a diagram yesterday, so I'm actually probably just going to copy that one. It might save me a bit of time. Because I've already done the whole paper, I just want to do it again with you guys. Here we go. I'm going to just copy this diagram, and then we're going to do it together. Okay, copy, so paste. Okay, so this is the diagram I've drawn. Okay, and we've done it, it doesn't matter which way you do it, but make sure it's 1, 2, 3, and 4 linked like that. The reason is we've been told T12, 1, 3, 2, 4, 3, 4. So we know 1 and 3 are linked, we know 1 and 2 are linked, we know 2 and 4 are linked, and we know 3 and 4 are linked. But there's no T14. Okay, so 1 and 4 we assume are not linked, not directly anyway. You have to go via 2 or 3. 3 and 2 are not linked because there's no T32, et cetera, okay? So make sure you draw it like that. Okay, so now we're assuming that the transport network is empty. All right, so what that means is if it's empty, that means we know what T12 is. T12 is 4 plus, it's empty, so it's plus 0, which means 4 minutes. Okay? T13, similarly, is 5 minutes. T24 is 3 minutes, and T34 is that coming up? Yep, 4 minutes. Okay? All right, and fortunately for us, there's no like sneaky, basically the time it takes to get from 1 to 2 is the same as from 2 to 1. 1 to 3 is the same as 3 to 1. The equations are the exact same, okay? All right, so now let's just draw that onto our diagram. So to get from 1 to 2 is 4 minutes. To get from 2 to 4 is 3 minutes. To get from 3 to 4 is 4 minutes. And to get from 1 to 3 is 5 minutes, okay? All right, so pretty straightforward. And that's in both directions. All right, so I will just kind of make that clear. It's not always going to be the same. In this question, it actually will change. But for now, it's just always the same. Okay. So now, for each OD pair, determine the minimum path tree. Okay, so basically we've been given 4 pairs here. We've been given 1 to 2, 1 to 4, 3 to 2, and 3 to 4. Okay, so fastest route, we'll say, or minimum, yeah, we'll just say fastest routes, okay? So, and what I chose to do was I just labeled each path. So we're going to label this one path. So that's path 1. We'll call this path 2. We'll call this path 3. And then we'll call this path 4. Or you could just literally, there's another way to do it, but I think that this works. Okay, yeah. So path, so the first OD pair is 1 to 2 would be path 1 is the fastest way, okay? 1 to 4 is, so 1 to 2 is easy because there's only, like, you're obviously not going to go all the way around. You don't even really need to check. 1 to 4 is where you now need to check. So there's now 2 ways to go from 1 to 4. You can go like that, or you can go like that, okay? So you can either go, it will take 4 plus 3 minutes, so 7 minutes, or it will take 5 plus 4 minutes, which is 9 minutes. Okay, so obviously you will take the one that is 7 minutes. So path 1 plus path 4. Okay, 3 to 2, again, this is not, they're not next to each other, so you need to actually check. So you could either go like this, which is 4 plus 7 minutes, or you could go like this, which is again 9 minutes. So we will choose path 3 plus 4. Okay, is that what I've written here? Yeah, part 3 plus 4, yes. And then 3 to 4 is the last pair, and that one again, they're next to each other, so obviously it's just going to be path 3. Okay, so that is how you do this question, and we've clearly listed the pair, the path, sorry. So not much more to do for that one. Okay, so I'll let you guys copy down while I look at the next question.
Okay, so
Yep.
this is just for every node to another node, right?
Yeah. Well, the nodes, the OD pairs listed here.
Oh, they gave us a node.
Yeah. So they've given us certain pairs. Let's just check though.
I didn't see that.
I think we're still recording. Good. Okay. Okay, so continuing on, and I'll share this, I'll maybe ask him to put the link in the description or something, I don't know yet. Okay, so now we have the next question, all or nothing, and this one was challenging. I actually think I may have left this last year, because it was like quite a daunting question, but I did figure it out this year, so I know how to do it now. So basically, the question is assign all trips to the minimum path determined in part A for the OD pairs and estimate link flows, link costs, and the total system travel time. Okay, so it will help us if we actually have this diagram again. So let's copy this diagram back. Okay. So, are we showing still? Yeah. Okay, so there's this this is the diagram. Okay. All right, so we are, okay, from this diagram, link flows. Okay, so basically what we need to do, okay, so this question has like a lot of steps. I actually don't really know why it's 6 marks. I feel like it should be probably more. I feel like part A should be less. Okay, so what we need to do is basically, there's a few steps, okay? So first of all, we need to figure out the link flows, okay? Because there are 8 links, okay? There's this link going that way, and then there's the link going this way. There's the link going that way, and the link going that way, and so on. So there's 8 different links, and we need to figure out how many vehicles use each link. That is the first somewhat annoying part. So, okay. So from, all right, so what I'll do is I'll copy the table from earlier, because I feel like it's going to be hard otherwise. So let me take a screenshot of, actually, I'll just write it. Okay, so 1 to 2 is, so 1 to 2 was 600. 1 to 4 was 1,000. 3 to 2 was 1,500. And 3 to 4 was 1,700. Okay, so basically, let's now kind of put everything onto the diagram. All right, so I'm gonna move this a bit, so because this diagram's gonna suddenly get very crowded. So from 1 to 2, we know we have 600 vehicles. Okay, so the best way, again, as always, is just to draw it out. 600. I'm gonna write I don't know, V, okay? From 1 to 4, we know we have 1,000 vehicles, okay? So remember, which one did we choose to be the fastest way to get from 1 to 4? It's either this one or that one, okay? And remember, we ended up going with this one because this one's 7 minutes. So that means we now add 1,000 going that way, okay? So I'll choose green. 1,000 vehicles going from 1 to 4, okay? And then we have 3 to 2, okay? So we have 1,500 going from 3 to 2. We chose this way, if you recall from earlier. So I'll choose this color, 1,500 vehicles. 1,500 vehicles. And then 3 to 4 was 1,700. There's only one route there possible. So we put 1,700 vehicles. Okay, so now we kind of have visualized where all the vehicles are moving. Yeah, this is something I was doing like at work, because I work in transport. So it's like this kind of understanding this is very important for traffic modeling, which the first half of the course is all about traffic modeling. So if you become a traffic modeler, it's like an introduction, I guess. So we've now done that. Okay, so now basically we want to plug it into our equations. And we want to figure out the link costs. Okay, so what I did was I literally wrote up an entire, I wrote up every single, so I'm going to do that now actually, so link costs. So from earlier, okay, we were given 8 equations. All right, I'm going to write them all out and then we're going to actually fill it out. So T12 equals 4 plus X12. T13 equals 5 plus X13. And I'll just be quick. You guys copy down while I do it. Okay, so that took a while, but now we've written all of them up. Okay, so now we're just writing out how much each link is costing us. Okay, so the first one, all right, so the number of vehicles going from 1 to 2, we could see is 1,600. Okay, so it's 4 plus 16. Okay, and this is where it's important to know it's in hundreds, because imagine you didn't know that, and then you're going to suddenly be like, oh, it's going to take you 1,604 minutes to go from 1 to 2. So that's why it's important to know that. Okay, so this ends up being 20 minutes.
Sorry.
Yep.
What does link cost mean?
So link cost is just their way of saying time, basically.
Oh, okay.
The time, so the cost in time.
Okay.
Yeah. So we found link flows. I mean, I guess we haven't explicitly written it out. So I guess if you want to be very explicit, you could actually write out. In fact, why don't we do that just to be I actually did it yesterday, so I'll just copy it in from yesterday when I was doing this. So here, this is the link flows. Just if you want to be, so link flows. Okay, so that's the link flows, and now we do the link costs equals 20 minutes, okay? So 1 to 3 is empty, so it's just 5 minutes because there's no cars. 2 to 4 was, and this is where you have to be careful. So it was 3 plus 10, which is 13 minutes. It's not 3 plus 25. So you might be tempted to add both, but this one is actually 4 to 2, not 2 to 4. Okay. So if we were to do 4 to 2, it'd be 3 plus 15, which is 18 minutes. Okay? All right, and so if we just be really quick here, so we get 4. So 4 is 4 plus 32, 36 mins. 2, 1 was 4 mins. 3, 1, nothing is doing 3, 1, so it's just 5 plus 0 equals 5 mins. And then 4, 3 was also 4 plus 0 equals. Okay, so most of them are empty, but we end up with 20 and 13 and 36 and 18 are the ones where cars are actually using them, basically. Okay, so that's that. But we still need to find the total system travel time. All right, so I've come up, this is the equation that we use. So what is total system travel time? Well, why don't we just think about it from first principles? Total system travel time is basically the total time that all travelers experience. It's not like, because of course what you're probably tempted to do is just literally add, like, and I think I almost did this as well, is just add all of this. So 20 plus 5 plus 13 is, I don't know, whatever, like 65 minutes or 85 minutes or something. But it's not quite that, because remember, like, no one's actually using 3.1 and no one's using 1.3. So it's like those travel times aren't being experienced. So you want to actually express what's being experienced. So the equation ends up being basically the sum of all the times on all the paths times the number of vehicles actually using that path. Okay, so what we end up with is total system travel time, I'll do it like that, equals, so it would be 20 times 16, because 16 vehicles use T12, plus 5 times 0, so it's going to take a while. 5 times 0 plus 13, how many use 2 to 4? It was 10. How many used 3 to 4? It was 32. How many used 2 to 1? It was 0. 3 to 1 was also 0. 4 to 2 was 15. And 4 to 3 was 0. Okay, and we times by 100, because remember, just do it like this, it's easier. We times that by 100, because it's in hundreds of vehicles. So if we just did that, then we would be removing the hundreds of vehicles, because hundreds of vehicles are experiencing it. And if you were to do that, you would end up with 187,200 vehicle minutes. Okay, so that's how many minutes all, however many cars that is, like 35,000 or something vehicles are experiencing. And then if you want to put that in hours, you would get, I got 3,120 hours. Okay, vehicle hours. All right, any questions? There's still more, unfortunately. This question's really long. I think we're still recording. I think it's recording, yeah. Hope to God the audio works. All right. Cool, so we'll keep going. The next question is check whether user equilibrium is achieved after the all or nothing assignment in part B, and show all the calculations and justify your answer. Okay, so I defined user equilibrium yesterday, so as opposed to rewriting it, I'll copy it in from yesterday. In fact, I could probably just copy all of this. Nah, we'll do it manually. Okay, so user equilibrium. So basically, I think you learned this in like week 3 or week 4. But what is user equilibrium? Well, first of all, any used route must be equal to one another. So basically, well, I'll explain with the diagram. All right. So let's say this is path 1. This is point 1 and point 3. It helps to actually understand how user equilibrium works. Okay. So let's say this path takes 5 minutes and this path takes 10 minutes. Okay, basically, so user equilibrium is the concept in traffic engineering that there will never be a better, faster route, okay, because of equilibrium. So if you think about when you're driving between two places in peak hour, like there's not really a route that is better that no one is using, if that makes sense, okay? If you're going from like Ryde to the city, your only route is Victoria Road, and there's no secret hidden other route, because if there was, people would have discovered it already, and it would take the same amount of time, if not longer. That's basically the idea. Okay, so basically, let's say everyone is using this route. We'll say everyone's using this route, and no one is using the other one. That would break user equilibrium because there is a faster route that no one is using. Okay. Yeah. So that's kind of the fun. That's actually I kind of explained number 2 instead of number 1. But let's say people are using both. Okay. That wouldn't make sense because number 1, the first part is faster. The first part is taking 5 minutes. So if people were using both, what would actually happen is, so let's say off peak, the bottom one takes 10 minutes and the top one takes 5 minutes. In peak hour, what would actually happen is this would end up taking like 7 minutes, and then this would also end up taking 7 minutes. Or actually, no, it would probably be better to say 10 minutes. They both would end up taking 10 minutes. Okay? It's not possible for a different path to be faster. Okay? The whole point is that everything ends up taking the same amount of time. Okay, and no unused route can be faster, basically. It can not be cheaper. All right, so that is what user equilibrium is. Let's now actually check to make sure everything is all right. All right, so what I wrote yesterday was that, I might actually just look at this. I've already written it all up. So number 1 is satisfied because there is only one route between all the points. Okay, so what I'm trying to say here is we assigned all traffic going from 1 to 2 is only taking one route. And all traffic going from 1 to 4 is only taking one route. And all traffic going from 3 to 4 is only taking one route, and so on and so forth. So point 1, which was that any used route has to be equal to one another, that is satisfied. But now we need to check if there is any unused route that is actually faster. Basically, are the cars actually taking the best route? Okay. So what we'll do is I'm going to copy this diagram, and we will actually kind of just, I would rather us do it manually rather than us just look at this. Okay. But that's my answer from yesterday. That's what I'll upload later. Okay, so we're going to draw on the new link costs. Okay, new link costs. All right, so I'll just draw them all on for you, but basically from earlier, from the previous question, it took 4 minutes to go that way from 2 to 1, 5 minutes to go from 1 to 3, 36 minutes to go from 3 to 4, and then 18 minutes to go from 2 to 4, from 4 to 2. Okay, and then this was 20 minutes. This was 5. This was 4, and then this was 13. Okay? So now we actually need to test to make sure that the cars aren't getting ripped off, basically. All right, so we're going to draw out a table. So this is a little bit tedious, but it's just what the question's asking. All right, so we're going to test each route. Current and alternative. Oh, it's a bit cramped. Sorry, I'm very nitpicky. All right. So, the 4 paths we're testing are 1 to 2, 1 to 4, 3 to 2, and 3 to 4. Okay. All right. So, currently, if we go back to part A and we check, or part B, and we check what route we told everyone to take, we told people from 1 to 2 to take, they just go directly, basically. And so now, after we put them all on that path, now the time is 20 minutes, okay? It's ballooned. So it's no longer, so from earlier, from part A, before there were any cars, it took 4 minutes. Now that we've added all the cars, it now takes 20 minutes. Of course, that makes sense, right? I mean, when you're driving a peak hour, it's slower because there's more cars. Now, that is if we go that way. Now, there is actually an alternate path. So no one going from 1 to 2 is using this alternate path, but there is an alternate path, and that is what we need to check to see if number 2 is fulfilled. Okay, so this is the alternate path. It's obviously crazy. Why would they do that? But we got to check. Okay, and it would be 5 plus 36 plus 18, which is 59 minutes. Okay, and obviously that is slower. So they are using the fastest route. So everyone is using the fastest route, and it's fulfilled. Okay, so if we kind of fly through this one ends up being 33. This one ends up being 54. Okay, it's the same kind of mentality for each, as I just explained, and this one ends up being 36. The alternative here is 5 plus 36 is 41. Okay, so we're fulfilling it here. So people going from 1 to 4 are using the fastest route. All right. Okay, and now for this one, 5 plus 20 equals 25 minutes, and you can see a problem here that they are actually getting ripped off. So they're not using the fastest route. So I guess in my example, it'd be like if a secret like underground free road opened between like Ryde and the city, basically, and no one was using it. Like we know that is impossible. So that means we've done not we haven't done something wrong. You're doing the question right, but like the way we've set it up and our assumptions are obviously wrong because we're not using user equilibrium. Okay. And then this one, so it's actually fine here, 5. So the last one's still actually okay. So it's only one of the links where it's broken. But that means it's broken altogether. If it's broken one place, then it's broken. All right, so user equilibrium not satisfied. Okay. All right, so continuing on, because I think I'm taking too long on this question. Glad I started at a hard question. I kind of knew I'd do this. So now assume only the OD pair 1 to 4 is active in the given network with a total demand, so I'll scroll up in case you guys are still copying, with a total demand of 2,000 vehicles per hour. Due to ongoing construction work on link 1-3, the actual travel time has increased beyond its normal value. Determine the minimum actual travel time at which all travelers will choose to only use path 1 to 4, resulting in user equilibrium where 1 to 4 is a unique route used. Okay, so we're going to draw it out another time. So we're literally just drawing this diagram non-stop. It's a bit insane. All right, so, and we've missed a line somehow. How did that happen? I don't know what I did. Okay, so we don't know how long this path takes. Okay? So basically, 1, 2, 4. All right, so we know, all right, so 1, 2, 4, going like that way, okay? Right, hang on. 1, 2, determine the minimum, I'm just reading the question again, sorry. So, we don't know the cost for 1 to 3, but let's figure out the cost for everything else. So, we are told that everyone is going to use 1, 2, 4. We want everyone to use 1, 2, 4, all right? It's saying specifically path 1, 2, 4 needs to be the unique route used. Okay, so this one was x12 plus 4. So if we're assuming all 2,000 vehicles use it, it's 20 plus 4. So that means that takes 24 minutes. Okay? Similarly, this takes just the same working out. I'll just do it for you guys. That takes 23 minutes. Okay? As for this one, no one's using it right now. Okay? And we don't want anyone to ever use it. We want people to only be going 1, 2, 4. So this is 0 plus 4, which is 4 minutes. Okay? So this is one of those questions where it's hard to do it unless you really understand what the question is asking. It's basically asking us to figure out the value of 1 to 3 such that the best way to go is 1, 2, 4. All right? So put it one way. If this was like 100 minutes, all right, then this route takes 104 minutes and this route takes 47, is it? Yeah, 47 minutes, okay? That's just to put it one way. Obviously, if this was 100, then that's ridiculous, then no one's gonna use it. The question's asking, like, what is the minimum of T13 such that no one would ever use that, ever choose that route, Okay, so it's actually just a simple inequality, but it's just hard to wrap your head around at first. So as per user equilibrium, we need the path of 1, 2, 4 to be less than or equal to the path of 1, 3, 4. Okay, it can be equal. It doesn't matter if they're both the same, because it was basically user equilibrium is there can be no other route cheaper. So it's fine if it's the same, but it just can't be cheaper. All right. So we currently have that path 1, 2, 4 takes 24 plus 23 minutes, and then path 1, 3, 4 we don't know what 1, 3 is, but we know 3, 4 is 4. So 47 is less than or equal to T13 plus 4. So T13 is greater than or equal to 43. So minimum for T13 is 43 minutes. Okay? So that's the answer.
Sorry.
Yep.
Could you explain what the question is asking again?
Okay, no problem. This is a very wordy question. So basically, it's telling us that we want all 2,000 vehicles to go from 1 to 2 to 4, using that route. All right, so I'll read it again. So assume only the OD pair 1, 4 is active in the given network. Okay, so basically, first of all, we're ignoring everything else. We're literally just looking at 1, 4. Okay, so we're literally just looking at this trip. So determine the minimum actual travel time in which they will only choose to go this way. Okay, so we want to figure out, so as I was saying earlier, let's say this equals 200. Okay, that would mean to go this way takes 204 minutes, but to go this way takes only 47. Okay, so which one would people choose?
The 47.
Yeah, they would choose 47 because it's cheaper. So in a way, that is almost like user equilibrium, but we want the minimum. We want the minimum such that it's user equilibrium without it being like 200. Okay, so that's why we set up that inequality to find what the minimum is. Does that make sense now?
Oh, okay. So equilibrium is like a hard thing that has to happen, but we're trying to make it so
It's minimized basically.
the cheapest route is route 1 to 4.
Yeah, 1, 2, 4. So we want 1, 2, 4 to be the cheapest.
Yeah.
And we want to figure out the minimum time on 1, 3 to allow that to happen.
Okay.
Yeah. All right. Any other questions or everyone good? Yeah?
When we consider 1, 3, 4, why do we not consider anyone actually going on 3, 4?
Because we're told this is the only OD pair active. See?
Okay. Yeah, okay.
So we're assuming no one's using it. Yeah, that's why. Okay. Anyone else or everyone good? All right, just check the recordings. I think we are good. Okay. Hopefully it's recording audio. I think it is. I'm very paranoid. Okay. So continuing on. Remember, I'll upload these. I'll give the solutions to SevSoc so they can upload it. Hopefully they do. Okay, so this question, all right, so now we're kind of into Stream 2. So Stream 2 is a lot more kind of engineering. So if you guys are kind of, I don't know if anyone's curious about actually wanting to work in transport. What I do at work is way more to do with Stream 1 than Stream 2, but that's because I'm like on a traffic modeling team. The funny thing is I don't even really do traffic modeling because I kind of sit more with the planners. Stream 2 is like, I would imagine what like your traditional civils teams do. This is something no one tells you in uni, but civil in the industry means something very different to in uni, because civil in the industry kind of means like roads and like drainage and things like that. But in uni, it's like a whole umbrella. So Stream 2 is all kind of like what you would do if you're like on a civils team that's like building roads, basically. So it's kind of like your more traditional engineering, where Stream 1 is a lot more like traffic modeling and systems and problem solving and maths. So if you like Stream 1, do traffic modeling, do like CVEN3401, do CVEN3401. Stream 2, I'm not so sure what electives relate to Stream 2. So You are asked to design a horizontal curve with the smallest possible radius for a 2-lane rural highway in the Southern Highlands region of New South Wales. Each lane is 3.6 meters wide. Due to expensive excavation, a maximum of 12 meters can be cleared from the road center line toward the inside lane to provide for stopping sight distance. Local guidelines specify a maximum super elevation of 8%. Okay, so part A is, can this highway be safely designed for a speed of 110 kilometers per hour? And if not, what is the highest possible design speed? And you need to justify it. This question took me ages when I did it yesterday. Actually, this whole paper took a while, but that's probably because I had to actually get everything right. Otherwise, I'm teaching you guys the wrong thing, so there's a lot more pressure. Okay, so I'm just going to copy the diagram I drew yesterday as opposed to redraw it, and then I'll explain everything I drew. Okay. So this is the diagram I drew. Hopefully it's correct. Okay. All right, so for one, we are told each lane is 3.6 meters wide. It's a horizontal curve. That's why I've drawn a curve. We are told the lanes are 3.6 meters wide. We're told a maximum of 12 meters can be cleared from the road center line towards the inside lane. So we've cleared 12 meters, and then we've got some obstacle here. I don't know. It's in the Southern Highlands, so I'd imagine it's just trees. So we've got like just trees here, but before that, there's no trees between here and here. Okay. Okay, and then I've added a bunch of other things which will become clear as we go. Okay, so what is this question actually asking? And this is where you need to kind of understand what it's asking, because it actually doesn't explicitly tell you what you're testing for, but it mentions stopping sight distance, and it says, can it be safely designed? So when it comes to this, it's basically asking you, can we drive around this turn without like crashing into an obstacle if an obstacle appears? Okay? So these are the two equations we're going to need. So we need those two equations basically, okay? Put it there. Okay, so these are the two formulas we need. Okay, so what is stopping sight distance? Well, you guys, I think stream 2 should be a lot fresher in your minds because you just did the assignment. Has that already been submitted? It has it? Yeah. So this should actually this whole part should be more fresh in your minds, but I'll tell you anyway. So stopping sight distance is just like from the minute they see something ahead to putting on the brakes, will they be able to stop in time? Okay? And it takes into account reaction time, it takes into account a lot of things. So I actually did use this formula once at work, so it does come up. And then S is sight distance, which is basically the distance that they will see something ahead on a horizontal curve. Because if you think about a curve, it's not as easy because like it's a curve. Like when it's a straight line, it's very easy to like, oh yeah, it's going to be like, I'll first see it when I'm like 300 meters away. But if it's a curve, it's a bit harder because you got to actually do calculations based on the curve. So obviously, to stop in time, you need to see it before you start stopping. So you need S to be greater than SSD. So we're obviously going to need to assemble a lot of values here. So let me actually just show you. I'll just kind of just copy this again. Sorry, I know I keep doing this, but it's just easier than writing it all out. So these are all the formulas, all the values we need. Did it paste? There we go. So first of all, we just literally go one equation at a time. We'll do SSD first. We need RT. Okay, so RT is reaction time. If you look on your formula sheet, because it's obviously closed book, but you'll have like a formula sheet. If you look on that, we have RT is 2.5. Okay. If I was to actually get it up, I think it should be at the end here. So let me just go to it really quickly. So RT is 2.5. Now this is where I would say Divya would like give you kind of like, what's the word? Like slack, because the whole point is you could say it's 2, you could say it's 1.5, but you need to like justify it. So I haven't actually justified it, I probably should have, but basically the reason we say it's 2.5, okay, so if you're uncertain and the question doesn't say, this is where like kind of, I know this course might not seem like structural engineering, it might not seem like steel or concrete, but this is one part where it kind of is. because you always just assume the worst case scenario. Like in steel, we are always adding like tolerance and we're adding like all of that stuff to make sure we get definitely a strong structure. Same thing here. Assume the worst reaction time possible. So think about if you're driving and you see an animal on the road, if you take 2.5 seconds to react, that's actually quite slow. That you've actually taken a while. In terms of like, oh, I see an animal and then starting the brake, 2 seconds is quite a while. But you assume that anyway because like you're preparing for like the worst case scenario here. Like you're not preparing for your average driver. Maybe you're preparing for someone who really just isn't good at driving. I don't know. Okay. Speed is 110. This is where it's important to just like check the formula. It is in kilometers an hour. The formula uses kilometers an hour. The hint is that you got a V over 3.6. So if you see a 3.6, that probably means they're converting from kilometers an hour to meters per second. The formula already does it for you. D is the coefficient of deceleration. It's in one of the tables, and you just can assume it's 0.36. I have done what I have not done, which you need to do in your exam, is you need to actually justify why you chose 0.36. So just make sure you do that. We're not given a grade, so you can just assume the grade is 0. RV is the radius of the center line of the inner lane. So you can see I've drawn it here. So if this is like kind of the center of the circle arc, then the radius would be to there, okay? And so RV would just be equal to R minus 1.8, because if it's a center line, look, you can kind of see from the diagram, if the lane is 3.6 and then RV is to the middle, then RV would be just R minus 1.8. And then M is the distance of the obstacle, from the obstacle to the inner lane center line. I've drawn it here. This is M, because we know this is 12, okay? And we know this is 1.8. So the distance from the obstacle to the inner lane would be 10.2 as per what I've done there. All right. Now, there is one thing we actually don't know, because remember, I've written here RV is R minus 1.8, but we actually don't know what R is, which adds like a whole other like complicated thing here, okay? We don't know what R is, and we need to figure out what R is, because otherwise we can't do this question. So it actually specifically says that, what does it say? Smallest possible radius, yeah. You are asked to design a horizontal curve with the smallest possible radius, all right? So one of the formulas on your formula sheet is R. So need to find R. So need to find minimum radius. So R, one of the formulas is R equals V squared over E 127 E plus F. Okay? Now, we are given what E is in the question. We're told that the super elevation is 0.08. Well, we're told 8%, but we'll just convert it to 0.08. And then we can say that F is 0.12 using table 7.5. I'll just show you how I got that real quick. Table 7.5. Okay, so this is F, okay, side friction factor. So we're told 110 kilometers an hour. And you might be thinking, oh, is it cars or trucks? In this case, it doesn't matter. They're all just 0.12. Okay, so we just choose 0.12. So a lot of referencing the tables.
You would choose the design one, right?
Yeah.
The first one.
Yeah, you would. But in this case, it doesn't matter because they're all 0.12. So R ends up being 110 squared over 127 times, well, 0.0 times 0 plus 0.12 is 0.2. You end up with 476.38. Okay, and I found earlier that RV is just R minus 1.8, so we get 474.58 meters. Okay, so now we actually have enough information to find SSD. Actually, we already had enough information for SSD, but we didn't have enough for S. So we could have actually done SSD already. So let's find SSD.
Sorry.
Yep.
I guess I wasn't paying attention, but E is also a table, right?
E, it would be, but it's provided in the question.
Oh.
Yeah, it's provided here. Otherwise, if they don't provide it, then... And that was... The fact they provided it is kind of, I think, them trying to hint that you need to use that formula. So, SSD, using the formula I got up here, it is So we just kind of use all our assumptions. Remember to define why you've assumed everything. That's 6 plus 102.254 times 0.36. So remember, there is no G.
They say 0 or something?
Yeah, so when they don't say what grade is, then you just assume it's 0.
Okay.
So for other ones, you need to make an assumption, but for G, like obviously if they don't tell you the grade, you just assume the grade is 0. This question, she didn't give enough space. I don't know how you would do this question in the space she's given, so it's a bit strange. Oh, that's the wrong size. Let me just add another page. Okay. So SSD ends up equaling 208.72 meters. So now we find S. Okay, so S is equal to 474.58 times pi. So this is just literally plugging in using the formulas from earlier, because it's RV times pi over 90 times cos inverse 474. And then M was 10.2. Was it? Yeah. Over 474.58. And we end up with 197.4. Okay, and now we're in trouble because S is less than SSD, therefore not safe. Okay? Because, just to really explain it to you guys, if you see the obstacle 197.4 meters beforehand, and then you hit it, you need 208 meters to stop, then you're going to hit it, basically. So there's not enough time to stop. So this curve is unsafe, and this is why we have speed limits. So if you're ever driving on a windy road, that's why you can't go to 110, because you won't stop in time. But I'm sure that was probably obvious. So we're going to try 100. We're going to try near speed, because she basically has asked us, if not, what is the highest possible design speed? So let's try V equals 100. Okay, so R equals, so I'll kind of just fly through this. So we kind of use the same formulas from before, 127 times 0.2, which equals 393.7. So now we find RV. RV is the same as earlier, or not the same, but like same approach. Okay, so SSD is 2.5 times 100 over 3.6 plus 100 squared over 254 times 0.36, which equals 178.8 meters. And then S is 391.9 over pi over 90 cos inverse 1.9 minus over. And then we end up getting 179.2 meters. Therefore, so S is greater than SSD. It's very close. So you could probably make the argument that you should actually make it 90 kilometers an hour as opposed to 100. But you could say it. You could even just say like. The reason why I'm tempted not to do that, and I just want to say 100, is you'd have to redo all your calculations for the next part, which is why it's just kind of annoying how close it is. Unless I've done something wrong, this should be correct.
So you can just take 100 or?
I don't feel like she will mark you down if you just say 100, because it's not like an explicit thing, because the rule is just as long as S is greater than SSD. So therefore, so highest speed is 100. What you could do, if you're like unsure, is you could just write like a brief statement that although to be safe, 90 may be best. 90 may be best for more distance. But the reason why I don't want to say 90 is because you'll see for the next part, then you'd have to redo all your calculations. So I did originally say 90, but then you just have to redo everything for part B, and it's just annoying. So maybe just have a brief acknowledgement, but then just go with 100. You'll see in Part B in a moment. I think everyone seems to be nearly done. To be fair, Part B is actually pretty quick, and I'm not even sure. I think this is what threw me in the exam last year, is the marking allocations were kind of strange. So that whole question was 10 marks, but then the next question is 10 marks, and it only took me like 4 lines. It's possible I did it wrong, but if anyone spots an error, let me know. Okay, so let's keep going. So this is our new, I'm just going to copy in our new diagram, and you'll see in a moment what I'm doing. Okay, so now assume that the maximum clearance is reduced to 10 meters. Based on the design speed estimated in Part A, determine whether it is safe to design the highway under these conditions. Provide a clear justification along with all necessary calculations. Okay. So before this was 12 meters. That's the only thing that's changed. It was 12 meters before, now it's 10. Okay, that means everything goes down by a bit. This is 3.6 still. So that means this is now 6.4. It means M is 8.2. We're going to keep the same radius. And this is what I meant by you would need to redo all the calculations. Because for this question, you need the radius, and you would have to find the new radius if it was 90, which is why I just went with 100. So we're going to just stick with R. That's why it's even in different colors, because you can see I actually originally did it. I originally did it all in orange, and then I did it in red because I went back. So we're going to say R is 393.7, which means RV is 391.9. We already did that earlier. So now so SSD is unchanged. Okay, and the reason why is SSD relies on, if you were to have a look at the formulas, it relies on reaction time, which we haven't changed. We haven't changed velocity. We haven't changed the deceleration coefficient. We haven't changed the grade. So SSD is the same. But S is changed because S is RV, which we haven't actually changed RV. But we have changed M. What was it? Over 90. Cos inverse 391.9. We did change M, so that was 8.2. That's the only change. But chances are it's going to be unsafe because it was already such a small margin earlier, so it's probably going to be unsafe. I'm saying I know it is because I did it already. It's 160.2 meters, so S is less, which obviously means you don't have enough time to stop, hence unsafe. And that's the whole question. I don't know why that's 10 marks. So if someone spots, if I've missed something, I don't know why. Because this is the same marks as the previous one. Anyone?
Did they not ask to redesign it?
No. That's what I mean. They didn't ask to redesign it. So they literally just asked, is it safe? I can't see anything I've missed. And I think it's things like this that threw me in the actual exam. So maybe it's just meant to be an easy 10 marks. I don't know. Okay, so that's that question done. I'll just give you guys a moment.
Is it alright if I ask like how you get, you have 10 and then you did the 6.4, 3.6?
Because, so we've changed it from 10, so earlier it was 12.
Yeah.
Okay, and then we're told that the clearance is reduced to 10. Now, we were told the lanes are 3.6 meters wide.
Yeah.
So it's on the same arc. So this is 3.4, which means this has to be 6.4. 3.6, which means that's 6.4.
Yeah.
Does that make sense?
Yeah, and then with the R and I'm mostly asking just like to the very first, like how you find R and
We found R from this earlier. Remember, from here, this formula?
okay.
So R is V squared over 127 times E plus F. E plus F was 0.2. And then RV is just the radius to the inner lane.
The inner lane. And then you just, which is half of
The inner lane.
Yeah.
So I should have mentioned that radius is to the center of the road.
Yeah.
Okay? This is something that almost tripped me up yesterday. So remember that radius is to the center of the road, because I originally did all of these calculations thinking radius was to the edge of the road, and I only realized afterwards that it's not. So make sure you remember that, yeah.
It's just where the location of the car would be, right?
Like, you mean RV?
Yeah.
Oh, that's where RV would be, yeah.
RV.
Yeah. I never thought of, yeah, that is why. That's true. Didn't even think of that. All right, any other questions or? Okay. All right, I think we just better keep going. So a highway reconstruction project is underway in regional New South Wales to improve safety and reduce accident rates. The project includes a major realignment of the highway to support a design speed of 100 kilometers an hour. At one location along the route, a 240 meter crest vertical curve already exists. Survey measurements indicate that at chainage 0 plus 107.29 from the beginning of the vertical curve, the vertical offset from the grade line is 1 meter. So we've got to first assess whether this existing vertical curve satisfies the stopping sight distance requirements. And then if it doesn't, which spoiler alert, it doesn't, then you need to calculate the minimum required curve length to meet the SSD standards. Okay? This question, and then part B is just like evaluate to check that, if it meets all the design criteria. Part B is a lot easier, but part A is quite a huge one. And I took like 2 pages to do it. Yeah, so, okay, and honestly, it took me a while to actually set up part A. It's kind of challenging, this question. Okay, so I'm gonna I just want to copy the diagram in from when I did it yesterday. Okay, this is the diagram. So a crest curve, I originally drew a sag curve, which was very silly. Make sure you draw a crest curve. So a crest curve, it's literally like a crest, and then it's like it's in the name, a sag curve does that, okay? Because it's sagging, and then a crest, like if you think about when you're driving, and so this is the diagram I've drawn. All right, so the equation of a crest curve is just a parabola. So a crest curve just follows ax squared plus bx plus c. Okay, now the tangent line, so the so-called grade line, okay, because you were told here, the vertical offset from the grade line is 1 meter. So the grade line is basically the line that shoots off from where the parabola, or I guess the crest curve, begins. So the crest curve begins here, which means this is the grade line, okay? From where it begins, and then it just it's like the tangent. Actually, I don't know why I didn't just say that. It's the tangent at that point, okay? And the formula of the tangent there would actually just be bx plus c, all right? If you were to yeah.
You're saying tangent as the cross of both of them, right?
Wait, yeah, what do you mean? Yeah, it's tangential at that point.
Of both lines, yeah. 'Cause,
Yeah.
They use the word tangent in another context, which is kind of annoying.
Oh, where do they use tangent?
I forgot.
Ah.
But it's used somewhere else.
Okay.
Not to do that.
And then, so this is all explained in, I think it was like the week 9 notes. So then what happens is, at chainage 107.29 meters, which is here, the distance between the grade line, this is the grade line, the offset line, the tangent, and the actual parabola, the crest, the distance we are told is 1 meter at 107.29, okay? So how did I do this? So basically, y equals ax squared represents offset. I don't know why I've drawn it, why I've done it like that. Offset. Okay, so 1.0, because we know this is we know that's 1 meter. Okay, so if we were to say at 1 meter equals a times 107.29 squared, so that means a equals, we end up with this ridiculously small number, 8.69 times 10 to the minus 5. Okay. So what do we actually need to do, and this is provided in your formulas, is we're trying to find the A to use in L equals KA, okay? Because the reason we need that is for our formula later, which you will do we end up needing? Oh no, we don't need the A. We need the K. Yeah, we need the K. We need to find K. So it'll probably actually what'll help and what I should have done originally. I'll show you the formula that we're trying to use, because then you'll understand why we're trying to get this. And we'll come back to this in a moment. But basically, so it's the same as earlier. We're still like earlier, like before. We're still trying to find stopping sight distance, and we're just trying to make sure that the stopping sight distance is lower than the sight distance. Okay, like before, the distance at which you see it is smaller, is greater than the distance you have to stop, basically. Okay, give me a moment. Yeah, so to find S, we need K, because K, S depends on these equations. Okay, so we need K. We need to find A to use in L, so that's the formula. L equals K. Because we know L. We've been told the length, so I'll explain this formula briefly. L is the length of the crest curve. K, forgetting what K actually is defined as. What was K again? I don't remember. But A is the absolute grade change. Does anyone have written down what K is?
It's like amount of grade change per like.
Yes, that's right. Yeah, it was length traversed for 1 meter or 1% grade change.
1%.
Yeah. Sometimes when you're just using these formulas, you forget what the letters actually mean, and you can't just use them. Yeah. So that's okay. So that's what we need. We need to find A, basically. All right. So first we need to find A. The slope anywhere. Okay, because obviously we're trying to find G1 and G2. Actually, I'll write out so you guys know what A actually is. A is the absolute change in G2 minus G1. Doesn't matter which way you write it because it's absolute. Okay. So that's what we're trying to find. But the only way to find that is we need to figure out what the grades actually are at those 2 points. Okay? So dy dx equals 2ax plus b. Okay, so that's the slope. This is the slope of the line. All right? So g1 equals dy dx 0, which equals 2a plus b. And, b, just b. What am I doing? Just b. Okay? And G2 is the grade at the end of the curve, which is 240 meters. So it'll be 480A plus B. So that means A equals 480A plus B minus B, which equals 480A. So now we know what A equals. All right, so A equals 480A. All right, so that means it equals, if we do 480 times 8.69 times 10 to the minus 5, A equals 0.041699, or in percentage terms, 4.1699%. So the grade changes by 4.1699. Oh, sorry, 17. We'll just say 17. Okay, cool. So now we have enough information to find K, but just like a brief recap of what we've just done, basically, we know the formula of a parabola is y equals ax squared plus bx plus c. That is the formula for a crest curve as well. So we find small a, and then we use small a to find big A using some differentiation. I think this setting up step is the most challenging part of this question. It took me ages to figure it out. So if you can just understand this part, then you're set, but it's kind of a bit of a challenge. It really relies on first principle thinking. Like, you can't really just like memorize it. Although, of course, if this exact question comes up, then you'll be fine. I don't know if it will, though.
No, you can't do it like this. No, it's a different approach.
All right.
Because in the assembly, it's actually two curves.
So now we can find K. Okay? So the formula was L equals Ka. Okay? So L is 240 equals K times 4.17. And the formula is you input A as a percentage. So you do put 4.17, not 0.0417. Okay? This is where, again, as always, it's very important to look at the formula sheet. So we end up with K equals 57.55. Okay, so that obviously took us ages, but we finally got K. So now we can find S. Now, we store recording. How long has it been? It's been an hour and 10. Okay. Now we can find S, sorry. Okay, so we have two equations here. We use the first one when S is less than L, and we use the second one when S is greater than L. So we're going to just try the first one, because we don't actually know what S is, so there's no way to test it. Okay, so 57.55 equals S squared over 200 square root of 1.1. Okay, and where have I got an H1 and H2? Again, it's from the tables. It's table 5.1. Assume H1 equals 1.1, H2 equals 0.2. Okay, we got it from the tables at the back. Okay, you just need to state why you're assuming that. All right, so you need to come up with that yourself. Yeah. Okay, so you can assume the worst case scenario, or you can assume because of this particular wording in the question. So we end up with, I'll just jump a few steps. We end up with 164.5. That is less than the length, because L is 240, so it's okay. We made the right assumption, we've used the right equation. Okay? So now we jump right into SSD, because again, what we're testing for is the same as a horizontal curve. We're testing to make sure that S is less than SSD, greater than SSD, okay? So what we end up with is SSD equals, so I won't bore you with this again because we did it just before, plus 100 squared over 25 times 0.36, which equals 178.81. But, well, once again, S is less than SSD, so it's unsafe. Which means we now have to redo everything, basically. It's really annoying. So, well, we require S equal to SSD at minimum. Okay? So in order to make this actually safe, we need S, because what is the question actually asking? Calculate the minimum required curve length. So we're told, no, you're not reducing the speed, you're not changing anything, you're just changing the length of the curve. Okay? So that is our variable here. So we're going to set S equal to 178.81 and work almost backwards, I guess.
So you find L.
Pardon?
You're trying to find
L.
L minimum now.
Yeah. Yeah. Okay, so now we have S is 178.81. So K, so we're kind of working backwards. To find L, we need K. A is still the same, we're not changing A, but we need L, and to find L, we need K. And to find K, we do this, 178.81. We keep all our assumptions about H1 and H2 the same. So we end up with K is 71.43. Again, L equals Ka, which equals 71.43 times 4.17. Therefore, L equals 297.86 meters. Okay, so hence minimum length is 297.86 meters, round to 300 meters for safety. Okay, you might as well, no harm. Okay, so we're gonna say it's actually 300 meters. All right.
Wouldn't you round down first of all?
No, you'd round up
Oh, right.
because we were trying to make the curve longer.
Okay.
Yeah.
No, that's it.
Because we've made the curve longer from before. It was 240 originally, and now it's 300. Okay, so for the next part, I'm just going to show you what I did last time. This is easier. So, what actually is part B? Part B is evaluate whether the current vertical curve meets all the curve length design criteria. So, by current, I interpreted them to mean before we redesigned it. So, we're using our previous values. Okay? So, basically, if you were to look at table 8.6, I'm not going to scroll there because this part B is 3 marks, to be honest. But if you were to scroll to these two tables, are the two tables that concern vertical curve. Okay, so table 8.6 is about appearance. So there's 3 requirements. All right, at 100 kilometers an hour, a minimum grade change of 0.4% is required. What we actually see is 4.17%. So 0.4% is the minimum, and we well and truly clear that. Now, we also need a minimum curve length of 80 to 100, and our current is 240. This is before we redesigned it. Currently it's 240, so that's okay. But the minimum K is where we kind of get broken. We need a minimum K of 50 or of 200 to 250, and ours is just 57.55, which is not okay. Now, the important thing is this table is actually just about appearance. So we could actually still be fine if we look at the actual design, like what's required for safety. So when we look at the design, the minimum K when RT is 2.5, if you look at table 8.7, it's all arranged by reaction time. And we assumed 2.5. And the minimum K is 71.4. But what we currently got when we did our calculations was 57.55, which again is not okay. So other than failing SSD, the curve currently also fails minimum K. All right? Great, so the good news is we've now done the 3 hardest questions in this paper, and we'll just do the 3 easiest ones. I wanted to start with the hardest so we could take our time on them. And yeah, those 3 are pretty hard. No problem. Yeah, so those 3 are the hardest, I would say. So let's move on to the easier ones. Question 6 is a net earthwork question. It's actually quite easy. I would say this is the easiest topic, and it's almost funny that it's like in week 10. Because it's literally, first of all, doesn't belong in this course. It just doesn't make sense it's in this course. Yeah?
Do you want to take a 5-minute break, or are you running out of time?
Oh, you know what? Yeah. That's a good idea, actually. Okay, someone has suggested we take a break. So let's take a break. Yes. We'll scroll back to the previous page. And I'll keep the recording going because I don't want to stuff it up. So for those watching on YouTube, just fast forward. All right. Anyone have any questions during the break? Or? I'll get the QR code up for. Actually, I lied. I think I will pause the recording. All right. Bye-bye. Oh, it didn't pause. Wait. All right, I'm back. So here is a QR code. I'll tell everyone else. 1 moment. All right, guys. So I have just made a QR code for 2025 plus 2024 papers and solutions. Can someone test to check if this works?
Yes.
I think everyone is right now. And if anyone, it should go to my OneDrive folder. It should have 4 things in it. What does that have to do? Is it working, guys?
No, yeah, it works, Sharon.
It worked? Was there 4 files in there?
Yeah.
Okay. All right, so just you guys who are watching as well. So basically, um, let me think. So we've got the 2025 paper in there, which Divya gave you this year, and then we've also got the My Solutions. Now, I've also got what I think is the 2024 paper. I don't know for sure that it is, but I think it is. It doesn't really matter if it is. I've just called it that anyway, just to make it easier. And then last year, Sue, she was one of the demonstrators last year, so you can definitely trust her solutions. I'm not even a demonstrator, she actually was. She did solutions for all of us, so she was like, what I'm doing for you guys, she did it for us. And so her solutions are in there, the paper's in there. So I don't believe you guys have that paper, so that's the crucial thing. The 2024 paper in that drive, I don't think Divya gave it to you, so I'd definitely do it because she doesn't know you have it, so she might recycle from there, I don't know. Yeah, and Sue also had a recording, which is on her YouTube channel. Let me find the channel. Here we go. So, no. Where did it go? Oh, you guys, I'm sharing. I forgot I was sharing. Okay, wait, let me find. Okay, so her YouTube channel, I'll link it for those watching online. I'll tell them to link it. But so if you're watching this right now, I'll tell them to put it in the description. But let me just tell you guys what her channel name was, and then it should be on there. And then we'll begin again. My internet's so slow. So her channel, if you literally just search CVEN3401 2025 T2 CVSOC crash course recording, it should come up. Yeah, I don't know why I wouldn't. Let me see if I do that, what comes up. Oh no, it doesn't. Why doesn't it? It's weird. It must be because it's not an unlisted video, is it? Okay. Oh no. Well, I can't think of a way to share it with you guys. Maybe when they upload this recording, just go to the description of the recording, and then I'll tell them to put a link to Sue's video as well, so that you guys can see hers. For some reason, it's not on the CVSOC page, her one. I don't know why. I don't know what happened. Okay, so we'll just continue. You can watch her recording later. To be honest, you have her solutions now anyway, so that's probably more than enough. Okay, so it's already 4:15, and we don't have very long left. I think, how long do we have this room for? Anyone? How long do we have the room for?
I don't think there's anyone after us. is it?
True, yeah, what am I saying? It's like stew bag. Okay, fair enough. I still don't want to go too over, because I, of course, also have to study for exams and stuff. So I'll try and, like, fly through the rest. I deliberately did the 3 hardest questions first, so that was not an accident. So, question 6, I was in the middle of saying earlier that it makes no sense why this is a transport subject, a transport question. It's like way more like 2101 coded. In fact, I actually think this, sorry, I don't know who's people, you guys. Yeah, this is a way more 2101 kind of sub question, but for some reason this is in transport. I don't really know why. But I'll show you guys how to do it just quickly. I'll probably just go through how I already did it. Because this is not very, this question's like 3 marks in my opinion. So definitely like just kind of be prepared. If she asks this, like it's just 3 marks in my opinion. But with that said, like you need to do it once. So try and do it when you go home. Once you've done it once, it's very easy. It's not like those horizontal curve where like a million things to consider. Like this is like, if you've done it once, you've done it every time, basically. So we've been given a diagram. It would help if let me see, can I display 2 pages side by side? I don't think I can. It would be great if I could. I don't think, how would I do that? Let me give it a try, actually. I think I know how I can. It's so much effort, though. Wait. I will. One moment. Let me, Actually, no, it's fine. It's too much effort. Okay, so basically, so we've been given these. I'm just going to scroll back and forth. It's going to be a bit annoying, but just bear with me. So we've been given all of these station points. So this one is at 0. This one's at 100. This one's at 200. This one's at 300. And this one's at 400. Okay? So we basically put the station points into our table here, 0, 1, 2, 3, 4, 400. Okay? Now, between 0 and 100, so first column is distance. Okay, so we have distance, fill, and cut. Okay, so the distance of fill between 0 and 100. What does that mean? Well, that just means how much fill is occurring between 0 and 100. Well, there's fill occurring for that whole length. Between 0 and 100, we are filling, sorry, the fill would be here, sorry. We are filling the entire time, okay? So it's 100. Then between 100 and 200, we're filling the whole time, so it's 100 again. But then between 200 and 300, we're not filling the entire time because we actually kind of dive down and we're not filling anymore. Okay, we go from fill to cut. So we need to figure out the distance transition. Okay, so yeah, you can see I have 100, 100, and then I have 51.06, and I'll show you how I got to 51.06. Okay, so basically you pretend that we're at like it's literally just similar triangles. Okay, so at station point 200, we're at 2.5. And then at station point 300, we're at just 2.3. Okay, we know the full distance is 100, but we don't know where the actual split is. So we'll just call this x, because it's x that we're looking for, and we know the full distance is 100, so that's 100 minus x. Okay, so if we do a bit of similar triangles, x over 2.5 equals 100 minus x over 2.3. Okay, now I don't want to really solve that this very second. So if we were to actually do it, it would be x is 51.06 or so. Okay, and then, so that is what this is here. This ends up being 51.06. And then if you do the subtraction, this ends up being 48.94. So what that means is between 200 and 300, for 51.06 meters, we are filling, and then for 48.94 meters, we are cutting. Okay? And then it's the same logic with this one here. Okay, 67.65. Okay? You'll note these two don't add up to 100. It's because for some reason, the very first one, we're both filling and cutting, which is really annoying. But it's not too big a deal because you go from 2.3 to 1.1, and you do the exact same thing. Okay? In terms of, yeah, I'll write out fill and cut. Okay. So I would say, honestly, the distance part's the hardest part, and even that's not very hard, because the fill and cut part's much easier. So in this one, you just put the areas, they've given it to you. So we're told at 0 that the fill cut, the fill volume is 8, 35, 55, and then 0, 0. So see, it's 8, 35, 55, and then nothing. As for cut, it's 25, 0, 0, 50, 55. It again lines up with what we have here. 25, nothing, nothing, 50, 55. Okay? So then we have double area. So double area is just the areas combined. Okay? Very easy. Volume is where we get a little bit harder, but even then, not too much. All right. So there are two rules that we need to use. There's trapezoidal and there's pyramidal. Okay, we use the trapezoidal rule if neither of them is 0. Okay, so we would divide by 2. And then if one of them equals 0, we would divide by 3. All right? So in this case, both of them are greater than 0, so we multiply them together and then we divide by 2. This one of them is 0, so we multiply them not multiply them together. We multiply it by the length. Okay, so here we multiply 25 by the length, but it's over 3 because one of them is 0. Okay, because this is 0. Same thing here. The length is 90, area is 90, and the length is 100. So 90 times 100 is, well, it's obviously 9,000. But then we divide it by 2 because these are both greater than 0. Here, obviously, it's 0. And you kind of just keep going, all right? What we get is we get a total fill of 7,586.1. We get a total cut of 66,629.42. All right? Okay, so I've then, basically, what is the question actually asking? We found the total fill and the total cut. The question is actually asking, calculate the net earthwork required. Okay, what does that even actually mean? Well, I've written out these formulas for you guys. Net basically just means the total fill minus the yield. Okay, now what is yield? Yield is the total cut minus the compaction. And so there's a million things. Compaction basically means the volume that we've compacted. Okay, so it's not just total fill minus total cut, because some amount of compaction will actually occur. Okay, we are told in this question that there is a compaction of 10%. It just so happens that what I've written in my notes is the same in this question. It's not always going to be 10%. In this question, it actually is. So if you plug it into the formula I've provided here, net equals total fill, which is 7,586, minus the yield. And the yield is the total cut, which is 6,629, times 1 minus the reduction factor, which is 0.1. And you end up with that. So this is the net earthworks required. All right? Any questions? Okay.
Positive means you need to bring soil.
Yes, pretty sure. I never thought about that, but yeah, it does. You would need to, yeah, because you're filling more than you're cutting, yeah. Okay, so we'll go back to the start now, and we should be done in like the next 15 to 20, I think. So I'll do question 1 first. Question 2 is really easy. Question 2 is not hard at all. Okay, so question 1. Question 1, I'm just going to talk through this. I'm not going to actually write anything because I'm tired. And also, these are the easiest. The first 2 questions are the easiest 2 in the whole paper. So, question 1 is a model of the relationship between speed and density in vehicles per kilometer for a particular roadway is, for some reason, it's a piecemeal function, which is a bit weird. And the weirdest part about this piecemeal function is they don't even meet at 70, if you notice. So I don't know what that's about. I don't know if that's intentional. I cannot imagine why they wouldn't meet. You'll see in a moment what I mean by that. So what is the free flow speed? Well, remember, free flow speed means the average speed of a road when the traffic is low. So here, when traffic is low, it just means K is less than 70. So it just so happens that the free flow speed is also 70. So the free flow speed is 70 kilometers an hour. That is the speed you can go at if there's no other cars on the road. The jam density. Well, jam density means the maximum density before all flow breaks down. In other words, it's when the speed is 0. Okay, so we are told that when K is greater than 70, Vs is 100 minus 0.68 K. So set Vs to 0, because that's jam density. You get 0.68 K is 100, and then so you end up with K is 147.06 vehicles per kilometer. That is the jam density. All right, I'll give that a moment. All right, I think that should be enough time. Determine the density at maximum flow. This is a classic example of first principles, where even if you don't remember the formula for maximum flow, just remember this formula, which should be on your formula sheet. This is like the fundamental flow density speed relationship. It defines everything in transport, or at least in traffic modeling. Q equals KVS. Okay, so VS just means speed. K is density, Q is flow. Now, the equation we have is Vs equals 100 minus 0.68 K. But we're trying to find the density at maximum flow, and our equation has not got flow in it. So we're going to actually just put, what on earth is that noise? So we're going to put flow into the actual equation. So we're going to sub in Vs equals Q over K. So the reason we do Q over K and not Q over Vs is obviously we're trying to find the density at maximum flow. So if we subbed in Q over Vs, then we'd lose density. So do Q over K. Q over K equals 100 minus 0.68 K. Q equals 100K minus 0.68 K squared. So that is our equation. Okay, flow is dictated by 100K minus 0.68 K squared, but we want the density at maximum flow. Okay, so dq to K is just calculus 100 minus 1.36 K. So when there is no so when dk is 0, 1.36k is 100, so you end up with the maximum density, the density at maximum flow is 73.53, okay? So, yeah, that's it. That you don't need to test if that's the maximum because, I mean, the equation is a concave down parabola, so you know it'll be a maximum. Just thinking back to like year 11 maths. Yeah, so that's how you do that one. So to visualize what this means, well, basically, what this means is every road will have like, obviously when a road is empty, that's its maximum speed. And when a road is completely full, that's its minimum speed, right? But you want to figure out the maximum flow, which is basically, if you think of it like if you think of a road, there will be a certain number of vehicles where you're getting the most vehicles through per hour without like ruining the road. Okay, like the M4 might be able to move 20,000 vehicles an hour, but it would not be able to move 40,000. Once you put 40,000 vehicles on that road, then it won't move. No one was moving, okay? It's the same, so that's kind of the concept here. Like there is a certain optimum value. If you put 0 vehicles on the M4, then the speeds are like maximum, but no one's on it, so you're not getting any flow, okay? So there's a certain middle ground, and in this case, the middle ground is 73.53 vehicles per kilometer. Okay, that is the middle ground. That means you're moving the most cars through, but you're also not breaking the road. Okay, and that's like literally traffic modeling. It's like trying to figure out what that perfect sweet spot is. And then maximum flow, look, it's just, you can figure that out yourself, I'm sure. You just take the K and then you put it back in the equation and you get 3,676 vehicles an hour. Then we're asked to actually graph it. And this is where it's really a really weird graph because it's piecemeal. So it's, for some reason, broken at 52.4. If you guys can spot if I've done something wrong, please let me know. I don't know why it is that way. It seems weird. I think it's just the way it's set up, okay? But that is the equation. That's how you would graph it. And the other weird thing is the graph paper makes absolutely no sense, the scale she's given us. So yeah, I don't know if she does this to kind of like torture us, because it just like makes you think you've done something wrong. Because you could double it, but then if you double the scale, then it's just ridiculous. It's just like so weird. I don't know why. Anyway, yeah, label it, put the axes labels. She also told you to label parts A to D. You can't really label part D, so I don't know how you would label that, because part D is flow, but it's a speed versus density graph. Okay, so that's that graph, not too hard. The next question is very easy. I think we'll be done in like 5, and then you guys can ask questions. Okay, so question 2 is basically a new commercial complex is planned, I'll zoom in, is planned at Barangaroo with a total floor space of 0.85 million square feet. I don't know why it's in square feet. It leads me to think this is a different question, and then it's just been replaced with Barangaroo. Maybe it's an American question. I don't know, from a textbook. It's really weird that it's in feet. It doesn't actually affect the question, so it's fine. The allocation of floor area and trip generation rates are given below. So even if you hadn't done this course, this shouldn't be too hard. It's like just literally like, you figure out the trip rates, okay? So basically, in Barangaroo, there are 3,200,000 square feet used, okay? So it's actually 3,200,000 square feet, okay? And 8,000 people are going to the residential. So that means if you were to convert that, for every 1,000 square feet of residential space there are 2.5 trips being generated, okay? And this is genuine traffic modeling. This is like stuff you actually do in the industry. Retail, I mean, it's obviously a bit more complicated than this. This is like very simple, but retail would be, if you do the same thing, 8.6 trips per 1,000 feet squared. Services is 5.2, and so on and so forth. Okay, now we split it into the given proportions. So we're told 0.85 million square feet. 30% of that is for residential, so that's 255,000. What was the, sorry, let me scroll here so I don't have to keep zooming in and out. It was 40% for services, so that's 340,000, and it was 15% for retail, so it's 127,500. Then the remaining area was allocated to leisure, and they have not told us what leisure is, so I've ignored it. If you said leisure was cultural facilities, that'd be fine as well. Just have a statement. I don't think she'll mark you down if you ignore leisure, as long as you actually acknowledge why you ignored it, or why you included it. Like you could write, I'm going to assume leisure is cultural facilities, but honestly, I don't know what leisure means. It's not defined. Okay, and then you apply the trip rate, so you know, you divide everything by 1,000, so every 1,000 feet generates 2.5, so it's 255 times 2.5, 637.5. Their services and retail, you end up with a total of 3,502 trips, which seems reasonable, I think. I think this is daily. That seems reasonable. I have no sense of how big 0.85 million square feet is. I don't think I would even if it was in meters. So, yeah. And that's it. Okay, great. We're done. Anyone have any questions? We actually finished early. No? Okay, I'll probably stop the recording then. All right. Bye. Hopefully it worked.